Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at white noise. Turns out that there's a whole class of undesirable signals that are best characterized as white noise random processes. The white noise random processes that you will encounter throughout your career depends upon the particular field of engineering or electrical engineering that you're going to ultimately pursue. I'm an optics guy, and in the optics world, the white noise processes that we commonly have to contend with are things like shot noise, spontaneous emission noise, beat frequency noise, and another thing called thermal noise. Turns out that thermal noise is a white noise process that pretty much everybody in electrical engineering has to contend with at one time or another. So today we're going to begin by talking fairly generally about the properties and characteristics of white noise, and ultimately we'll spend some time talking specifically about thermal noise. All right. What are some characteristics of white noise? White noise. First of all, it's a stationary random process. Stationary. Also turns out that white noise processes are zero mean. All right. And they have a constant power spectral density at all frequencies. All right. So what I mean by that is if this is my spectrum, my noise power spectral density at all frequencies is a constant. And in fact, and this is zero frequency here, and this has units of hertz, my noise, white noise power spectral density is usually written this way, N0 over 2. So I would have an N0 over 2 there. All right, now this model, this power spectral density model that is constant for all frequencies from minus infinity to plus infinity, it's not exactly physical. It would take infinite power to create such a white noise process. But white noise model is good if the noise is white, at least over the bandwidth of the message or filter that we might be interested in characterizing. All right. So strictly speaking, having a constant power spectral density over an infinite frequency bandwidth is not really physically realizable, but it's a pretty good model if the noise is white, at least over the bandwidth of the message or filter we're examining in the presence of our white noise. Okay. What about noise power? So we've got a white noise process. And what I'm interested in is the noise that exists in some bandwidth B. Bandwidth is always, of course, defined based on positive frequencies. All right? So noise power in bandwidth B hertz. So my units here are hertz. And we'll call this P sub n of b. This is clearly 2 times the integral from 0 to b of my noise power spectral density. And that's just going to be n naught over 2 times 2 times b, which is n naught b. And this thing will have units of watts. Okay? Units of watts. So this is actually something we can typically measure. The question is, how do we know what the value n naught is? Well, it turns out you can design an experiment to pass a white noise process through some reasonably ideal low-pass filter, measure the power passed through that filter. You know the bandwidth of that filter. You can divide the power divided by the bandwidth, and I will get access to n naught. So n naught can be measured. All right, not going to get into the details of how we would set up an experiment, but let's just suffice it to say that n naught can be measured. Another thing that I want to point out, and I don't know that I've done this before, I just want to point out, I'll do it in the context of white noise, but I want to point out something related to the units of power spectral density. All right, so for a white noise random process, the power spectral density is just n naught over 2, but this has to have units of watts per hertz. Okay? The units here, watts per hertz, is true regardless of what my random process happens to be. For power spectral density, the units is always watts per hertz, because what I'm doing is I'm spreading power over a frequency spectrum. Well, my units, a watt is a joule per second, but 1 over seconds is hertz, so that could be written as joule times hertz over hertz, and the hertz cancel out. Turns out that the units of power spectral density could also be called joules. Sometimes you'll see that. Not often. More often than not, you'll see people characterize the units of power spectral density as watts per hertz. I actually prefer watts per hertz because it demonstrates that I'm spreading power over a frequency spectrum. But if you simplify watts per hertz, you come up with joules. So if you see that, don't be freaked out. Okay. Well, what about the autocorrelation? The noise power spectral density is a constant. That's a constant. The autocorrelation is just the inverse Fourier transform of my power spectral density. And the inverse Fourier transform of a constant is just that constant times the delta function. That's that. My autocorrelation, therefore, looks something like this. It's just, let me use another color here just to kind of demonstrate this. My autocorrelation is just a delta function centered at tau equals 0. All right? What that means, remember, autocorrelation is a measure of the similarity of a random process to itself at some earlier or prior instant in time. What this tells me is that white noise is so completely random that it is completely dissimilar to itself at any other instant in time. Knowledge of white noise process right now tells me nothing about the white noise process in the future or in the past, no matter how close I am in the future or in the past. You could call this totally random. Okay? That's one characteristic of a white noise process. All right. White noise through a linear system. White noise through a linear system. So I've got some linear system with a transfer function, capital H. I've got a noise process coming in, and I've got some filtered noise at the output. So white noise in and filtered white noise at the output. What can I do with that? Well, I'm going to look at the cross spectral density. This is a relationship that we've seen before. The cross-spectral density is the cross-spectral density of the input to the output equals the input power spectral density times the transfer function. This is N naught over 2 times H of F. Taking the inverse Fourier transform of that, I get the cross correlation and what I end up with is N naught over 2 times the transfer function, times the impulse response, little h. All right, recall that the transfer function equals the Fourier transform of the impulse response. Or, rearranging, I can say that my impulse response equals 2 over N naught times the cross correlation of the input noise process to the filtered noise output process. That's kind of important. Remember I said earlier, without regards for the details of how I'd actually perform the experiment, I can experimentally measure N naught. I could also set up an experiment and take a filter, some unknown black box type filter with an input and an output, and I can apply a white noise process to the input and set up some data collection schemes where I collect the input process, samples of the input process, pass that white noise through my linear system, and use a similar data collection scheme to take samples of the output random process. I can then take my samples of my input and samples of my output random process, plug that into MATLAB. MATLAB's got a cross correlation function that it'll be happy to perform for you instantaneously. Perform the cross correlation and divide by N naught, multiply times 2, and I know then the impulse response of my unknown black box linear system. Many of you may have been in a lab at some point or another and seen an oscilloscope or maybe a signal generator or a spectrum analyzer that has this unusual function called a white noise generator. Well, this is one reason why I might be interested in having a white noise generator. I can apply white noise to an unknown black box linear system, cross-correlate the input and output, and get access to the impulse response of the system. It's pretty handy. Okay, another thing we can do with white noise is talk about the noise equivalent bandwidth. noise equivalent bandwidth. I'm going to do this both for low pass filters and band pass filters. We're going to start by looking at a low pass filter. Low pass filter first. And over in the upper right hand corner of the screen we see a low pass filter. The actual, this is just something I sketched. The actual filter is represented by the solid line, and equivalent ideal filter is shown by the dashed line. You'll notice that the equivalent filter and the real filter have equal amplitude at the origin, H0. All right. So what we're interested in doing is finding the bandwidth of a fictitious ideal low pass filter through which equivalent noise passes. Okay? All right. So, and keep in mind that the ideal fictitious low pass filter so my fictitious filter by convention will have an amplitude H0 equal to the modulus of my true transfer function evaluated at 0. That's what that means. All right. So let's write down the power spectral density at the output of such a filter. Maybe we can just draw this a little bit here. What I've got is I'm going to have a noise process at the input and a filter noise process at the output. Okay? So I've got some noise process at the input, pass through my filter with transfer function capital H, and I get some sort of filtered process at the output. All right, let's do the math. The output power spectral density equals in general S x of f times the absolute value squared of my transfer function, and in this case this is N0 over 2 times absolute value of H squared, because we're talking about white noise. The power spectral density of the input is just N0 over 2. The output noise power equals, we'll say P sub N0, output noise power, is going to be 2 times the integral of N0 over 2, integral from 0 to infinity. Strictly speaking, I would integrate from minus infinity to plus infinity, but the the low pass filter process that I showed on the previous page was symmetric about the origin, so I can double the integral from 0 to infinity. Continuing on, my integrand is then just H of f modulus squared df, and of course my 2's cancel out. For my ideal filter, the output noise power will be integral from negative B sub n to B sub n of n naught over 2 h naught squared df. And remember, h naught equals absolute value of my transfer function of my real filter evaluated at 0. And integrating a constant, clearly this just becomes n naught h naught squared B sub n, where B sub n is my noise equivalent bandwidth. And I'm going to set that equal to that. All right. I'm going to set this is the power coming out of my ideal low-pass filter. I'm going to set that equal to the power coming out of my true actual filter. Solving then for Bn, my noise equivalent bandwidth, I get B sub n equals 1 over h naught squared, integral from 0 to infinity. That is my result. Okay? We'll do an example with this in just a few minutes. So my noise equivalent bandwidth in hertz, oops, not n sub z, h sub z, or hz, hertz. The noise equivalent bandwidth in hertz is given by that relationship. There's a time domain relationship for noise equivalent bandwidth that I'm going to derive for you in just a couple of seconds. But before I do that, I want to look at the noise equivalent bandwidth for a bandpass filter. Turns out the relationship is pretty much the same. Noise equivalent bandwidth in this case for a bandpass noise equivalent bandwidth for a bandpass filter. In this case, I'm looking at something that looks like this. Okay, zero frequency. This is going to be centered at frequency f sub c. This down here would be negative f sub c, and that is going to be h naught. In this case, h naught squared equals absolute value of my transfer function evaluated at fc. That's the only difference. Okay, that's the only difference. And we're going to set up and find an ideal equivalent low-pass filter whose bandwidth is the noise equivalent bandwidth. Okay? What we want to find is what is the noise equivalent bandwidth. All right. Well, once again, the output noise power is P sub n naught. And for the real filter, that's going to be 2 n naught over 2, integral from 0 to infinity, absolute value of h df. And just to remind you, this is the output power spectral density. This is the integral over the output power spectral density. This in all cases is S sub x of f times the absolute value squared of my transfer function. And in this case, it's just n naught over 2 absolute value of transfer function squared. All right, that I'm integrating over the output power spectral density. All right, and so this is just for the fictitious filter. So the first result here is for the real filter. For the fictitious filter, the output noise power is going to be 2 times the integral from fc minus b sub n over 2 to fc plus b sub n over 2, n naught over 2 h naught squared df. Once again, I'm integrating a constant, so the result is n naught h naught squared b sub n. This is the output noise power for my fictitious ideal filter, and I'm going to set that equal to the output noise power for my real filter. Setting those two equal and solving for my noise equivalent bandwidth, I get that. And you'll notice that that relationship is exactly the same as what we had for the for the low pass filter type characteristic. The only difference in this case is that for the band pass filter, H naught is found by evaluating the real filter characteristic at the center frequency f sub c, and in the low pass filter case, H naught was the filter characteristic evaluated at 0 frequency. Otherwise, they're exactly the same. All right. What about a noise equivalent bandwidth from a time domain perspective? Time domain analysis. Time domain analysis. This is for noise equivalent bandwidth. This is noise equivalent bandwidth, and I'm going to do it for the low pass filter case. All right. Well, first of all, I'm going to recognize that my my transfer function is the Fourier transform of my impulse response. And that can be written as the integral from minus infinity to plus infinity, h of t, e to the j 2 pi f t d, that is a t dt. All right, that is the integral relationship for the forward Fourier transform. Fourier transform integral. Okay, that's the Fourier transform integral. Well, very quickly then, h of 0 is just area of my impulse response. Okay? This is for a low-pass filter. I'm assuming a low-pass filter here, folks. Okay? H sub 0, which is my transfer function evaluated at 0, is the area under my impulse response. The second thing I'll recognize is that we recall Parseval's theorem. Parseval's theorem says that the integral from minus infinity to plus infinity of the absolute value squared of my impulse response equals negative infinity to plus infinity of the absolute value squared of my transfer function. All right, so this is Parseval's theorem. All right, so plugging these two things into my relationship for noise equivalent bandwidth, I get the following. Okay, that's my relationship. Now, you'll notice that this factor of 2 comes in because I'm employing Parseval's theorem in the numerator of this relationship, this time domain relationship for my noise equivalent bandwidth, whereas in the frequency domain characterization for noise equivalent bandwidth, I was integrating from 0 to infinity. Down here, I'm integrating from minus infinity to plus infinity. So I'm doubling my integral, so I need to divide by 2 in the denominator. All right, and as usual, my noise equivalent bandwidth has units of hertz. Okay, so I do want to point out that this relationship is a little bit different than you will encounter in your textbook, Cooper and McGillem. Cooper and McGillem assume they make the following assumptions. First of all, they assume that they have a real impulse response. And 2, they assume that h of t is equal to 0 for time less than 0. In some cases, these two assumptions are not necessarily incorrect. My relationship here on the bottom of the page is a little more general than Cooper and McGillem's relationship. Cooper and McGillem's relationship applies in certain cases, and we're going to do an example now where Cooper and McGillem's equation would apply. So, let's do an example. First of all, we're going to look at noise equivalent bandwidth for a simple low-pass filter. Okay? My transfer function is going to look something like this. It's going to be A over 1 plus J 2 pi B F. All right, where clearly H0 equals A. And my impulse response, which equals the inverse Fourier transform of h of f equals the inverse Fourier transform of a over b over 1 over b plus j omega. And that's the form of a inverse Fourier transform that you can look up in tables that I've provided you already. And this equals a over b e to the minus t over b times step function. Okay? And of course, omega here is 2 pi times regular non-radian frequency f. Okay? So here is a case where my impulse response is real and h of t equals 0 for time less than 0. My impulse response, for example, looks something like this. Okay, that's a kind of low-pass filter characteristics that Cooper and McGillum assume, as I pointed out on the previous page. For a simple RC low-pass filter, let me just remind you of this. For a simple RC low-pass filter, something that looks like this, resistor, capacitor, through voltage division, I can find that the transfer function is just 1 over 1 plus j 2 pi RC F. All right, this is just find this by voltage division. All right, and in this simple low-pass filter case, A would equal 1 and B would equal just the time constant RC. Okay? That's a time constant that would have units of seconds. Okay? So for the low-pass filter characteristic that we're looking at for this particular example, H sub 0 is capital A. Maybe this is an active low-pass filter. Okay, since it's got some amplitude A that's not equal to 1. All right, so let's find the noise equivalent bandwidth of this type of filter. First thing I need is the modulus squared of H. That's just H times H complex conjugate, and that's just A squared over 1 plus 2 pi BF quantity squared. The noise equivalent bandwidth then is 1 over H naught. H naught squared, integral from 0 to infinity. That, this equals 1 over A squared, integral 0 to infinity, of A squared over 1 plus 2 pi FB quantity squared df. Now I'm going to make a change of variables. I'm going to let x equal 2 pi bf, dx equal 2 pi b df. All right. Simplify a bit, I get 1 over 2 pi b, integral from 0 to infinity, 1 over 1 plus x squared dx. Looking this up in tables, I get 1 over 2 pi b times the arctangent of x integrated from evaluated at 0 and infinity. I just looked that up in tables. And then evaluating, I get 1 over 4b hertz. Okay, 1 over 4 times the time constant. Well, you might ask yourself, how does this relate to the 3 dB bandwidth of this low-pass filter? So let's look at that next. 3 dB bandwidth of my low-pass filter. The way we get access to that is we look at our transfer function evaluated at my 3 dB point. And I set the modulus squared of my transfer function evaluated at the 3 dB frequency equal to the modulus squared of the transfer function at DC divided by 2. That's the half power. And this equals a squared over 2. And I'm going to set that equal to Alright, so this much equals that much, and this equals that, and I'm going to set those two pieces equal to one another. Alright, it's pure simple algebra from that point on. You find that the 3 dB point, 3 dB frequency, is just 1 over 2 pi times b. Alright, so what we see then, another way of writing this is, well, recall that the noise equivalent bandwidth is 1 over 4b. In both cases we're talking about hertz here. One thing you'll notice is that in all cases with this low-pass filter, the noise equivalent bandwidth is somewhat greater than the bandwidth of the 3 dB bandwidth of my low-pass filter. Another way I can rearrange this a little bit, I can say that my noise equivalent bandwidth is 2 pi over 4 times f3 dB, or pi over 2 times my 3 dB frequency. Alright, that's a pretty handy relationship to know. Noise equivalent bandwidth for a low-pass filter is pi over 2 times the 3 dB frequency. That's kind of handy to know. I don't have to go through and calculate noise equivalent bandwidth. A lot of times I'll know the 3 dB bandwidth of a low-pass filter. If I know the 3 dB bandwidth of a low-pass filter, multiply that times pi over 2, and I get the noise equivalent bandwidth. All right. Okay. So I've told you that we were going to talk generally about white noise processes, and we've done so. And I want to spend some time talking about a specific white noise process known as thermal noise. Thermal noise. This is a white noise process. And it is due to the presence of compressed carbon resistors in circuits. So it's due to resistors. at least the Thevenin equivalent resistance. Due to resistors in circuits. All right? So basically what happens is this. If we're at any temperature above absolute zero, there's thermal energy that's agitating the electrons in compressed carbon resistors. So thermal energy causes agitation of free electrons in resistors. If those resistors somehow find themselves in a closed circuit, even in the absence of other stimulus, even in the absence of other signals or messages applied to that circuit, those thermally agitated electrons are going to move around inside of the circuit. All right? So in a closed circuit, small current will flow. Even with no signal applied. All right? In a closed circuit, a small current will flow even when there is no signal applied. It's very common. It's one of the reasons why in real sensitive circuits sometimes we set up cooling circuitry, thermoelectric coolers, liquid nitrogen baths, those kinds of things. We'd like to have our circuits running as cool as we could to keep down thermal noise. Another common way of referring to thermal noise is Johnson noise. All right, after an engineer who first examined the idea of thermal noise very early on. Most of the time you'll hear it referred to simply as thermal noise. Some textbooks, some authors prefer the use of the phrase Johnson noise. They mean the same thing. All right. The power spectral density S for thermal noise is, turns out, 2 kT, watts per hertz. T is the absolute temperature in Kelvin. In degrees Kelvin. K is Boltzmann's constant. And that turns out to be 1.38 times 10 to the minus 23rd joules per degree Kelvin. All right. Remember that watts per hertz is equivalent to joules. All right. Boltzmann's constant is expressed in joules per degree Kelvin. Temperature is in degrees Kelvin, so joules equals watts per hertz. The units match. Okay? Earlier we wrote the white noise power spectral density as N naught over 2. So if we did that, N naught in this case would be 4 times kT. So if I divide that by 2, I get 2 kT. All right. Thermal noise. thermal noise in a bandwidth B. All right, once again, I'm assuming a low-pass type situation here. All right, the noise in a bandwidth B centered at the origin is E sub t, thermal noise power, is 2 times the integral from 0 to B times my power spectral density. And this is just going to be 4 kTB, and that will have units of watts. Okay? All right. Now, very commonly when we encounter thermal noise and other white noise processes that corrupt messages and signals that we desire, we commonly represent these white noise processes as a noise current. So let's look at that for the thermal noise case. Thermal noise current. Now, you'll remember if this is some resistor R, the thermal noise, let me go over here, my thermal noise, which is 4 kTB, I'm going to write this as a mean squared current times resistance. All right. So in effect, there might be some noise current flowing through my resistor. So this is the RMS current squared, all right, or mean squared noise current. All right, and R in this case would be the Thevenin equivalent resistance looking into the terminals of some circuit. So this is the Thevenin equivalent okay, it's a Thevenin equivalent resistance looking into an input or output terminal of some black box circuit. Okay? It's the real part of the Thevenin equivalent impedance. So, just solving for my noise equivalent current. Okay, and this would have units of amps squared. That is my thermal noise current model. Okay? You'll notice that my noise current decreases if my temperature goes down, if my bandwidth goes down, or if my equivalent impedance goes up. So two handy ways of, if typically the bandwidth of my system is fixed due to other system requirements. Sometimes my bandwidth just is what my bandwidth happens to be in order to satisfy other requirements. I can't commonly fiddle with bandwidth in order to reduce thermal noise power. What I can do, though, to reduce thermal noise is cool the circuit or somehow increase the load impedance. Okay? Large loads, cool circuits, yield low thermal noise power. All right, so let's do a quick example here to get an idea of what thermal noise might look like. All right, let's just say I've got a real simple circuit here. R3, R2, R1, and I'm going to look into this terminal here, and I'd like to have an understanding of what my noise current looks like. All right, I'm going to assume that my temperature is room temperature, 290 degrees Kelvin. I'll assume something not particularly big for my bandwidth. I'll say 2 megahertz. And let's assume that R1 equals R2 is 10 ohms and R3 is 5 ohms. So my Thevenin equivalent resistance is R1 parallel to R2 plus R3. You can do that, turns out it's just 10 ohms. All right, so my noise equivalent power, or my thermal noise power rather, is 4 kTB. Plug all that in, I get 3.2 times 10 to the minus 14th watts. The thermal noise power is independent of resistance. And at first glance that looks ridiculously small. Why don't we even just ignore it? Well, my noise current is just 4 kTB over R, or my thermal noise power divided by resistance. And that's 6.4 times 10 to the minus 15th amp squared. Once again, golly, that looks just ridiculously small. Let's ignore it. Let's take the square root of that. So the square root of IN squared is IRMS for my noise. And that turns out to be 80 nanoamps, or 0.08 microamps. And that may actually be appreciable. Okay? Nearly a tenth of a microamp might be appreciable. The currents that we find inside of, say, cell phone circuits are really tiny. So, anyway, this is just a quick example to give you a feel for what thermal noise might look like. Even though the noise currents in some cases seem small, they really can be quite large. Let's do another example. Let's look at the thermal noise at the output of a RC low-pass filter. Output of a RC low-pass filter. All right, so in the absence of any other driving sources. So we've got a resistor and a capacitor, and we're not at absolute zero. So this is a noisy resistor. And what we're going to do is we're going to pretend that this has got an equivalent circuit that looks something like this. That's supposed to be a resistor there, folks. So in this case, I'm going to have a noiseless resistor, noise-free resistor, and I'm going to assume that I've got thermal noise driving the circuit. All right? And this is, just redraw this a bit. All right, so noiseless resistor. But thermal noise drives the circuit. And then I've got some output filtered noise, power spectral density. All right. The transfer function through voltage division is just, we've seen this before, 1 over 1 plus J 2 pi RC. The modulus squared, oops, I guess I should probably put an F there since I'm using regular frequencies today. My modulus squared of my transfer function is just 1 over 1 plus 2 pi FRC squared. All right, and so my output power spectral density is just 2 kT over 1 plus 2 pi FRC quantity squared. Okay? Let's go to the next page. My output thermal noise power output thermal noise power, P in naught, is going to be 2 times integral from 0 to infinity of my output power spectral density, and that is 2 times integral from 0 to infinity of 2 kT over 1 plus 2 pi f RC quantity squared df. Make a change of variables. I'm going to let x equal 2 pi RCF dx equal 2 pi RC df. Plug that in, and I get 4 kT over 2 pi RC, integral from 0 to infinity, 1 over 1 plus x squared dx. Once again, I looked that integral up in one of my tables, and I get 2 over pi kT over RC arctangent of x evaluated from 0 to infinity. And that's that. Okay, so my thermal noise power at the output of a simple RC low-pass filter circuit is just Boltzmann's constant times the temperature divided by the resistance and the capacitance. And my noise power decreases as temperature decreases and as my load resistance increases. Always keep that in mind. Okay, when you're dealing with thermal noise, cool circuits, and large real parts of my equivalent impedance are to my benefit. Okay. All right, a couple more topics to round out the day. I want to talk about a thing called the noise figure. Noise figure. Here's the situation we're looking at. I've got a broadband amplifier with power gain G. Power gain G, not an amplitude gain. And at the input, I have a signal to noise ratio. And at the output, I have an output signal to noise ratio. Okay? Signal to noise ratio is signal power divided by noise power. Okay? Signal to noise ratio is the ratio of signal power to noise power. Sometimes, if it's expressed in dB, signal to noise ratio expressed in dB, because signal to noise ratio is a ratio of powers and not voltages or currents. Since signal to noise ratio is a ratio of powers, in dB it's 10 log signal to noise ratio as a simple ratio. Okay? If we're dealing with voltages or currents, we use 20 log. If we're dealing with power ratios, we do 10 log. Okay? All right, so let's think about this. We're talking about a broadband power amplifier, something like if you have a home stereo, you have a power amplifier that drives the speakers, for example. The radio in your car has a power amplifier in its last stage that drives the speakers in your car. Your cell phones have the very last stage is a power amplifier that drives the speakers in your cell phone. That's the thing that you have that you adjust with a volume control is a power amplifier. It's a broadband power amplifier. All right, so notice what happens is the message, the desired signal or message, as well as the noise, are both amplified by the amplifier. Okay, both the incoming signal and noise are amplified by G. Amplification doesn't improve signal to noise ratio. Amplification does not. Simple amplification does not improve signal to noise ratio. Signal to noise ratio is also a measure of clarity. How clear is the signal? How clear is the signal compared to the noise that it's immersed in? So simple amplification does not improve signal to noise ratio or clarity. Worse yet, the amplifier will add in its own noise. could be, very likely, is thermal noise. So here's an experiment you can do. Go home, if you have a home stereo. Go home, turn all of the input sources off. Turn off your CD players, your MP3 players, whatever drives your power amplifier. Turn them all off. Turn the volume control on your power amplifier to 0. Turn your amplifier on, make sure it's connected to your speakers, and start turning the volume up. What you're going to hear, even in the absence of any signal driving your power amplifier, you're going to hear hiss coming out of those speakers. That's noise. It's probably mostly thermal noise because your amplifier is not sitting at absolute 0. You're mostly hearing thermal noise. Okay. Now turn the volume way back down to 0 on your power amplifier. Turn your power amplifier off. Plug in all the rest of the sources, your sources, and proceed as usual. I don't want you to blow any speakers. But your amplifier is going to add in its own noise. So as a result, in all cases, for a broadband power amplifier, the signal-to-noise ratio at the input is greater than the signal-to-noise ratio at the output. Okay? Broadband amplification causes a reduction in clarity as a rule. Broadband amplification reduces signal-to-noise ratio. The signal-to-noise ratio is better at the input than it is at the output because the amplifier tends to add its own noise. Okay? So the ratio of input signal-to-noise ratio to output is known as the noise figure. All right. In dB, if signal-to-noise ratio at the input and output is just expressed as a ratio, then F is just a number. In dB, we express it we again use the 10 log of my noise figure expressed in dB. So for example, just a quick little example here. Let's say that my input is got a signal-to-noise ratio of 4:1. My signal power is 4 times larger than my noise power. And let's say that at the output, the output signal-to-noise ratio is 3:1. All right. My noise figure is then okay. In this case, if my signal-noise ratio at the input was 4:1 and my output signal-to-noise ratio was 3:1, my noise figure would be 1 1/3 or 1 1/4 dB. That's pretty good. All right, remember 3 dB, a noise figure of 3 dB would mean that I would reduce the signal power by half compared to the noise at the output of my amplifier. In my experience, typically my experience has been that noise figures on the order of 2 to 10 dB are things I've encountered. All things being equal, if I'm talking about analog circuitry, I want to have lower noise figures. If I'm dealing with digital circuitry has got some natural immunity to noise. If I'm dealing with digital circuitry, I can deal with amplifiers that have higher noise figures. So, say digital, and this I want low noise figures for analog circuits. Okay? One last thing. What happens if I have multiple cascaded amplifiers? Typically, a final power amplifier that drives a speaker is preceded by one or more preamplifiers. So if I know the noise figure for one or more preamplifiers and my final power amplifier, how do I find the overall noise figure of the system? So noise figure for cascaded amplifiers. So it looks something like this. I've got a signal noise ratio at the input. I've got gain 1, noise figure 1. I've got gain 2, noise figure 2. Gain 3, noise figure 3, all the way up to gain N and noise figure N. And ultimately, I've got an output signal to noise ratio. Well, it turns out there is a relationship known as the freeze formula. Actually, it's S apostrophe. The overall noise figure equals F1 plus F2 minus 1 over G1 plus F3 minus 1 over G1, G2 plus all the way up to Fn minus 1 over G1, G2, all the way up to G of n minus 1. And in this relationship, my noise figures and my gains for each individual amplifier are expressed as ratios. Not dB. Okay? Just a little example. Let's say I've got 3 amplifiers and I've got 3 amplifiers and their gains and noise figures are expressed in dB. This one has a gain of 10 dB and a noise figure of 3 dB. This one's got a gain of minus 6 dB. It attenuates by a factor of 4. And it's got a noise figure of 6 dB. And I've got a final power amplifier with a gain of 40, which is what? 40,000? Something like that. And a noise figure of 5. Convert all that to just ratios. and I get 10.25 and 10,000. I said 40,000 earlier. A gain of 40 dB is a ratio of 10,000. Sorry. My noise figures are 1.995. That's about 2. And this one is 3.981. It's about 4. And 5 dB is a multiplicative factor of 3.162. All right. The overall noise figure is then 1.995 plus 3.981 minus 1 over 10 plus 3.162 minus 1 over 2.5, and that is 3.1579 as a ratio, or about 5 dB. The overall noise figure for this collection of 3 cascaded amplifiers is about 5 dB. What about the overall gain? Overall gain. All right, that's just going to be 10 times 0.25 times 10 to the 4th, and that is 2.5 times 10 to the 4th, or 44 dB. All right, this is clearly just gain 1 times gain 2 times gain 3, where I'm working with ratios here. Or, turns out I can also just add the gains in dB. That's 10 plus 40 minus 6, that's 44 dB. Okay? The gains in dB simply add. Okay. Well, I apologize for that being so long, but all those topics seem to go together, so I wanted to do it in just one single video instead of breaking it up. That is all for today. That's all I have to say about white noise for right now. As usual, if you have any questions, please feel free to contact me at your earliest convenience, and I will do everything I can to answer your questions as fully and quickly as I am able. Have yourselves a wonderful day. Bye-bye.